Hello, this is the hardware and circuit optimization workshop. We're going to be diving into how we try to reduce noise in a variety of ways. We've talked a little bit about error correction and error mitigation, and while there's no doubt that those are crucial elements of getting meaningful results out of quantum circuits. Another aspect is trying to reduce the noise in the first place. And we do that but through circuit optimization with regard to the hardware that we're actually deploying it to. So let's dive right in. So as before, we're going to save our account for the Qiskit runtime service with your API key and your CRN. All right. And then once we've done that, and we can initialize our Qiskit runtime service, and we can find the backends by typing service.backends. So here we see that we have Fez, Torino, and Marrakesh available to us. So let's take a look at the Torino backend. We can take a look at how many qubits are available on IBM Torino. It looks like we have 133. We can get the processor type, which is the Heron, which is the latest family of quantum devices that we have access to. And we can even see what are the basis gates on that particular architecture. While we frequently use a wide array of gates, Hadamard's X, Y, Z, controlled NOT, controlled Z, and some of the others that we've covered, all of these are actually accomplished by a set of universal gates on that specific architecture. So it seems that on IBM Torino, we have access to a controlled Z, an identity function, rotate on the Z, square root of X, and X. This can be useful to us as we're working and building our quantum circuits that we can target a particular architecture and construct our circuit in such a way that it makes the best use of the native gates. Now, another aspect that we can do sometimes is to use the least busy service. And what this means is that there's typically queues or waiting for us to deploy to the real quantum hardware. By using least busy, it will just put us to the device that has the least weight on it. This is good in a lot of ways. It allows you to more quickly get your measurements back whenever you do that API call to the quantum hardware. And there's a trade-off here. It's good for some quick prototyping, but oftentimes we will want to specifically target a specific quantum computer. That way we can characterize the noise in each qubit. So whenever I selected least busy, this time I'm getting IBM Fez. It's still the Heron architecture, and it has the same set of basis gates. Now, I talked about wanting to perhaps target particular qubits and how we lay out our circuit. To do that, there's a couple of methods that we can use. We can use just a basic coupling map. So I call backend.couplingmap.draw, and it shows me how these qubits are laid out. All right, each one of these nodes is a qubit, and an edge are two directly connected qubit pairs for your 2-qubit gates. This topology affects your circuits. If a set of qubits, of 2 qubits, aren't connected by an edge, that's going to require swaps, which means your circuit becomes deeper to swap those qubits around. This architecture is the heavy hex architecture, but we can also plot this with plot gate map, and I think this representation's a little bit nicer. But this shows you how these qubits are actually connected. So you can actually specify in your quantum circuit which one of your qubits is corresponding to each one of these specific qubits in the coupling map, and that can help guide you on what entangling scheme you use and how you are going about trying to, lay out your circuit. That way it's as shallow as possible. That way you're getting less noise. Another useful thing is the plot error map from Qiskit.visualization. So on this fake Brisbane backend, we get a layout of the qubits, and we also are able to see the readout error on each individual qubit. Furthermore, we can see the Hadamard error rate and the controlled knot error rate. So the 2-qubit gate error and the the single qubit gate error. And we'll see, like here between qubits 24 and 25, we have a very high C0 error rate, and here at qubit 95, we're having a high Hadamard error rate. So this can help guide you. These qubits will differ on their error rates and things. And just because one qubit has a higher measurement error or it has a higher Hadamard error doesn't necessarily mean that you don't use that qubit, but you use it in a way that you avoid that. So, qubit 95 here may have a high Hadamard error rate, but perhaps its error rate with entanglement isn't as high, and so you can use that. And the same goes for your measurement, that you may be able to use a qubit as an ancilla qubit where it interacts with the other qubits, but you don't measure on that particular qubit. Now, these are fairly high-level top-down views on this, but you can also dive in, and for each individual qubit, you can view its specific error properties. So here I'm just iterating through the first 5 qubits, but I'm calling qubit properties. And so with this, I can see the T1 error rates and the T2 error rates. And you can see there's significant variation in these and the depolarizing, dephasing properties. And so you can use that to inform what you use particular qubits for. We can also get an idea of what our median error is among these qubits. And so this is assuming that I'm using all the qubits in the system. But I can specify the set of qubits that I'm going to target, and I can calculate statistical measures on these qubits to understand that the median decoherence time here is 136 microseconds. That can inform me on how that's going to affect my quantum circuit with the time that my quantum circuit will take to execute. We can do the same thing for the T2. And some other aspects that we can call is the backend.target. So this is a dictionary, and it shows us all the functions that are available to us, our quantum circuit, on this particular hardware. We see the same gates that were available to us that we showed earlier: control Z, RZ, X, square root of X, identity. Okay, but also we have delay, that we can delay the execution of certain gates. We see reset, as well as you can do conditional formatting with quantum circuits, where you take a measurement from a qubit. If that measurement's 0, do this. If that measurement's 1, do this, etc. Then, of course, our measurement operation. Here, I'm iterating through, and I'm seeing what this single qubit SX error is. And I can see that the duration that it takes for this to occur, as well as its relative error. And we're seeing that qubit 0 here has, pretty high rate of error compared to the rest, at least 3 times higher than the next highest one. And so we can use this to inform what we use qubits for and whether that's the appropriate qubit to use that day. Here I'm taking a look at my 2-qubit error between various qubits. So I'm taking a look at my 2-qubit error, and it looks like the lowest 2-qubit error is between qubits 2 and 3 here. It has a 2-qubit error that's much lower than like these between qubits 0 and 1 and 1 and 0. But while qubit 0 has this small single qubit error rate, it has a high 2-qubit error rate. So we can use that to inform on if we want to lay out our circuit in the most efficient way possible on which qubits that we use. Another aspect of this that we should consider is that we can characterize how accurate our measurements are using this noise. We can have an idea of how clean and how much variance we are introducing into our calculation by characterizing this using things like Krauss operators. We can also characterize our measurement error, and I've said before that we can use qubits as an ancilla that we don't measure on. Maybe there's a qubit that we're entangling more than another. Maybe there's a qubit that we're not doing any single qubit operations on. Whatever the case is, but we can take a look at this measurement error. And earlier we noticed that qubit 0 here had high noise. It looked like qubit 1 had pretty low noise. Qubits 2 and 3 were really good. And then we take a look at this measurement error, and we're seeing that qubits 2 has really good measurement error, but qubit 3 doesn't. So, it's important to take a look at all these different factors and understand what we are assigning each qubit as and what you're using it for. This is that, you can do great error correction and error mitigation techniques, but, ideally we introduce as little noise as possible in our quantum circuit. And we can specify how we use each qubit to try to minimize that given our constraints. I can also get the median single gate error. My 2-qubit error, I can get that median value as well. So you can really do a good job of understanding what the current noise profile is on a specific quantum device, and you can tailor your quantum circuit to minimize that. Now, that specifying each qubit and designing your quantum circuit around the current noise profile on that circuit is one way to do a good job of minimizing that error. However, there are tools available to you that don't require necessarily that extreme level of specification. You can also use the preset pass manager and its optimization functions to reduce this error, or you can even combine them together. So for this, I'm using a fake backend. These fake backends are really useful in that you have a simulated device, but it's including the noise in that. So you can compare how the noise will compare between your ideal circuit in simulation versus with the noise folded in. I'm teaching a class. I'm always encouraging my students to understand what the noise looks like as they scale up so they can make intelligent decisions with the error mitigation techniques that they're applying. So here we're using Brisbane as our fake backend. It has 127 qubits, and this is from the Eagle family. We'll notice that instead of a controlled Z 2-qubit gate, it has this ECR. These things matter because they can inform which gate choice you're making in your actual quantum circuit. Now, to highlight how helpful these optimization techniques can be, we're going to take a look at a GHZ circuit. So this is a pretty basic circuit where we place one qubit in superposition, and such that it would be measured as 0 50% of the time and 1 50% of the time. We then do a controlled NOT operation to the other qubits, such that if this qubit 0 is going to be measured as 0, qubit 1, 2, 3, and 4 will also be 0. And then if qubit 0 is 1, it will flip these other operations to where they're all also 1. So the output we'd expect from the sampler on this particular circuit would be 0, 0, 0, 0, 5 zeros, or it would be 5 ones. Any other bit string, 0, 1, 0, 1, 0, or anything like that, isn't what we should expect from this. So let's take a look at what the optimization in our preset pass manager here can do. The preset pass manager, remember, is this translation between your quantum circuit and the machine. So I run this preset pass manager on my circuit at optimization level 0. Okay, and let's take a look at what the circuit looks like whenever it's taken from our basic circuit into the gates that are native on that machine without any optimization. So I have a fold of 30 here, so that means there's 30 layers of gates before it wraps over to the next line. So that looks like we have almost 90 layers of gates here for our circuit that started with 5. So we can see that what looks like a pretty shallow circuit to us is significantly deeper if we just try to directly translate that to the hardware without doing any optimization. Now, if instead this time we run it with optimization level 2, and you have optimization levels 0 through 4 available to you, our circuit is much, much shallower. 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So we've taken it from almost 90 down to 25 layers. So that's a significant improvement, better than 3 times better on the depth we have. So, we can roughly approximate that we're going to cut our noise to a third of what it would be without this optimization. So it just really illustrates how important these optimization steps are there. We can also profile these to see how this actually turns out if we run these on a noisy simulator. All right, so I'm going to specify a sampler with the backend is my fake backend that I specified earlier, and I'm going to pass as my pub to this circuit 0 and circuit 2, where circuit 0 is with optimization level 0 and circuit 2 is optimization level 2. All right, and that's this job ID. Remember, your job stores all kinds of data about this run, not just your circuit, but the results, the job ID, how many shots were done, what the values of each shots. There's a lot of data in that job. But if we just want to view the results, we can pull out the results and get counts on result 0 and result 1 here. And let's take a look at what this ends up looking like. So, we have our peaks on all zeros and all ones here, with the blue being ideal, the orange being no optimization, and the green with our optimization. And we see that by applying our optimization, we're getting much, much closer to our ideal value on the anticipated ones. And we can also see how frequent this orange appears on these values that we wouldn't expect from this quantum circuit. And that's the way that we're representing our noise there. But we can do even better. Earlier here, you see that in our design of our circuit, we have this star layout. So we have our qubit that we place in superposition, and it is the control for the other 4 qubits. However, we don't have a qubit that's directly connected to 4 other qubits on our architecture. On our architecture, we have that heavy hex lattice like this, where at best we have a qubit connected to 3 other qubits. And so that means that a lot of these extra gates that are being added in that result in this circuit depth of 90 without optimization and 25 even with optimization. A lot of this is doing swap operations where it's moving these qubits around, that way they can be entangled with each other. If we take a little bit more care and thought with how we design our circuit, we can combine it in a way such that we don't have to introduce those swap operations. So here we place 1 qubit in superposition, we connect it to 2 neighbors, and within those 2 neighbors we connect to 2 neighbors. What this allows us to do is to accomplish the same circuit without swaps. Now, this propagation is, we're squaring the probability of this error occurring, but at the same time, by so drastically reducing this depth and cutting out all these swaps, we gain far, far more than we lose. So if we, instead of doing that star configuration where we have 1 qubit connected to 4 other qubits and we have to do swaps, if we use a method that our physical quantum computer can do without the swaps, hopefully we'll be able to even further reduce. So the original synthesis with that star layout, we had around 25 layers of gates. And this new setup where we used this chained layout, we have 11. So we even halved again our circuit depth. And by just being a little bit more careful with how we lay out our circuits and how we apply these gates, we can really, really, really make improvements here. So, we'll run this with our original circuit and our new circuit, and let's take a look at what the results look like. So, once again, blue is our ideal, orange is no optimization. Green is our very highly optimized circuit, but the one with the star layout where we didn't think about how the entanglement pattern we were applying translated to real hardware. And then red is with the circuit where we kept that more in mind. And so we see that we're even more closely approaching this ideal value that we can simulate. And so not only on our positive samples, but we also see the reduced representation in all these negative samples for our new circuit, that we're drastically reducing the error. So we are able to, by being a little bit more careful, we can go from nearly 90 gates to 12. So it's taking the time to think about how your circuit applies to the real hardware, evaluating what the actual error rates are on the qubits of that hardware can be all the difference between you having a quantum circuit that's not useful or meaningful towards what you're trying to accomplish, where that's dominated by noise, and one where you can begin to demonstrate the potential of quantum. Thank you all very much. Have a good day.